So now we'll start with question number 5. It was a beautiful problem of combinatorics. Now this question had this clause that there were 2000 coins at the vertices of a regular polygon of 2000 sides. Now a goblin is allowed to take these steps. Say there are 3 consecutive coins. Now he can take coin of these 2 positions, keep one for himself, and the remaining coin he can place here. So effectively there will be 2 coins here, 0 coin here and 0 coins here. Alright? He is allowed to make any number of such kind of steps till the time he can do that, and whenever it is possible that he has any such configuration where there is a coin, and whatever be the configuration here, he has to necessarily make a step at whichever position he wants. So finally, what is the minimum number of coins that he can take and what is the maximum number of coins he can take? This was the question. Now how to move ahead with the solution for this one? The minimum case seems very obvious in the sense that if you try to juggle with these coins, then he can take, say these are some consecutive positions, then he can take away coin from here, or he can like place 2 coins here, he can take away coins from here. So these two positions do not have any coin. Similarly he can do here also, so that there are 2 coins here. Now in case this is the situation, he cannot do anything with these 2 positions from this situation, and similarly he will keep on doing that. So he is taking a combination of 3 positions, 3 consecutive positions, and trying to take all the coins possible, as least number of coins as possible, and therein he can cover 666 into 3, alright, which implies we'll be left with 2 coins in the end. And from the positions where there are 2 coins left, there is no coin here, but there are 2 coins here, and similarly there is no coin here, but there are 2 coins here, he can make 2 more moves. So in all, the least number of coins that he can take is 668. Now the difficult part here is how to prove that he cannot take any lesser number of coins. The 668 will be the least number. Now that we can prove showing this particular thing, that how many odd number of positions are there and how many even number of positions are there. Based on that, attacking on the positions, we can prove that particular part. For the second part, which is maximum number of coins that he can take, by trying out few numbers, the intuition says that the maximum number can go very high. As it turns out, the answer is 1998 out of 2000 coins. Now obviously he cannot take all the 2000 coins because he will be left with at least 1 coin. So it could be either 1999 or 1998 or lesser number. Now 199 we can easily exclude. Why? Because there is an invariance shows this thing, and this we could actually find in the start only, that say if we have 3 coins like this, in the next position there will be 2 here and there will be no coin here. So let us assume I number these positions as 1, 3 and similarly odd positions, and this one as 2, 4. So this is even, this is odd. So sum of total number of coins at odd positions and total number of coins at even positions, their mod with respect to 3 must remain same. What does it imply? If I take away 2 coins from here and put 1 coin here, so we add 1 here and subtract 2 here, right? So effectively mod 3, with respect to 3, if we check the remainders still remain the same. So with respect to 3, remainders of sum of number of coins at odd positions and sum of number of coins at even positions, the remainders will remain the same. So using this, we can easily prove that 1999 coins cannot be taken, because that will invalidate that invariance. So now it comes out to show how we can take 1998 coins. Now that can be done this way. We'll take the following steps. So these are the coins. We'll put 2 here, remove these 2. There are coins here also. In the next case, we'll take coins from these 2 positions and put here. So effectively we have no coin here. Okay, we have 1 coin here. All right, we have 1 coin here. We have no coin here, right? And we have 1 coin here. So in all, if you see, this looks more like no coin, 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 no coin. So we'll reach to this configuration, which is kind of a symmetric configuration with respect to this line. This whole thing becomes symmetric, and now we'll work separately on this part, which will be a symmetric solution for this part, and using that we can show that we can take 1998 coins. Now I invite Abhinav here to show this part of solution, to complete solution. He will come here and show this in details. All right, thank you.
So first we'll prove for minimum. So whenever, so let us say we consider only the even vertices. Let us say they are P1, P2 up to P1000. These are all the even vertices. So whenever we do an operation on an odd vertex, let us say on this, then we remove 1 coin from the adjacent 2 even vertices, that is 2 consecutive even vertices, and add 1 coin here. So let us say we do this operation at most 333 times. So every time we do an operation, we remove coins from 2 even vertices. So if we do this operation at most 333 times, we remove coins from at most 666 even vertices, because like there might be repetitions also. So there are at least 334 vertices where we have not done the operation. So let this number be k. So so assume that we haven't done the operation of P1. So it means that we must have done the operation on P2, because if we have not done the operation on P2 also, then it means that we can do the operation here. So it means that we have done the operation on P2. And if we have done on P2, we must have done on P3 also, because we do an operation on 2 adjacent even vertices and we haven't done on P1. So it means that we must have done on P3. So there might be some more which we have done the operation on, and let us say there is some Pt where we haven't done the operation. So it means that t is greater than or equal to 4, and between any 2 consecutive even vertices where we haven't done the operation, there is a gap of at least 2. So let the gaps be like a1, a2 and so on up to ak. So we know that all ai's are greater than or equal to 2. So this means that a1 plus a2 up to ak is greater than or equal to 2k. However, it is also 1000 minus k, because every vertex which has been done an operation on, it is counted exactly once here, because it is counted once in exactly one in some gap. So it means that this is also equal to 1000 minus k. However, 1000 minus k, this means that 1000 minus k is greater than or equal to 2k, but that's a contradiction, because we assume that k is greater or equal to 334, but we get that 1000 is greater than or equal to 3k. So that's a contradiction. So it means that we can have done at most, so it is wrong that we have done at most 333 operations. So we have done at least 334 operations on odd and similarly even vertices. So we have done at least 334 into 2, that is at least 668 operations. Now we'll show that this is possible. So take this 111 and we will convert this into a 0 to 0. Now similarly we'll convert the next 1 1 and 0 to 0, and so we have gent of 2000 by 3 equal to 666 blocks of 0 to 0. So we have two more ones left here. Now we can do this operation on 2 and 1, and similarly here also. So it becomes 0 1 1 0 0 1 1 0. So we did 666 plus 2 operations, and now we can see that we can't do any more operations. So this is indeed the minimum. Now we show that the maximum is 1998. So we have 111, so we convert this into 0 to 0, and now we convert this into 0 1 1 0 and all ones. Now we will divide this into two halves. So when we do this operation on this one, it becomes a, so right now we have 101 and then all ones. Now we do this operation here, so it becomes 0 101 and then all ones. Then we do this operation here, so it becomes 0 0 1 0 1 and then all ones, and we keep doing this. So we then have 0 0 then all zeros, then 1 0 1. Now we do this operation here, so we get 0 0 all zeros, then 0 1 0. So we did this in the right half, like here, like here we did this to get 0 1 0 and all zeros. Similarly we will do this here to get 0 1 0 and all zeros. So we have only 2 coins left, that is we took the rest of the 1998 coins. So we have a construction for 1998 coins. Now show that we cannot take more than 1998 coins. So every time we do this operation, the number of coin, it decreases by 1. So let us say that we take all the 2000 coins. So it means that at one point we have only 1 coin left. However, we can't do the operation because to do the operation we need at least 2 coins. So we couldn't have taken all the 2000 coins. Now let us say that 1999 is possible. So we will take two numbers x and y. X is the number of coins at even vertices, and y is the number of coins at odd vertices. So if we do the operation on odd vertices, the number of even coins decreases by 2 and this increases by 1. And if we do the operation on the other one, then this increases by 2 and this decreases by 1. Either this is minus 2 and plus 1, or this is minus 2 and this is plus 1. So if we keep track of x minus y, it increases by 3 or decreases by 3 every time. And right now both are 1000. So right now it is 0. So it means that x minus y mod 3 is invariant because it changes by 3 every time. That is, it is a multiple of 3 every time. However, if there is only 1 coin left in the end, it is either 1 and 0 or 0 and 1. So x minus y is 1 or minus 1. However, both are not a multiple of 3. It means that is also not possible. So it means that 1999 is also not possible. So 1998 is only possible, and we achieved that. So it is the maximum and we are done.